Team. Thanks Adway, and thanks to the other organizers also for arranging this meeting. So this is work that I'm pursuing here with different students and postdocs. We're going to look at oceanic submesoscale. So we had quite a bit of introduction to ocean models through Gokan's talk and also Professor Goswami's talk earlier today and yesterday. So this is, I'm going to present some approaches to data-driven modeling of a specific set of scales in the ocean. And this is work done with students listed here. So Mayank is somewhere here. He's a PhD student. Kridin, Pustam, and Mausam are project students, the students who visited to work with us for 1 year. Mausam, I think, was here in the morning. He worked with me for his master's thesis work. And so these are a couple of papers that are in this direction, looking at the flow and tracer dispersion at oceanic submesoscale. So we'll see more of this in this talk. So you had a pretty good introduction to the ocean dynamics over the past couple of days. So the oceans, Gokan and others introduced this very well. Earth system, when you look at Earth systems, we have atmosphere, land, and the oceans. And as multiple speakers emphasize, ocean is a relatively slow component. So exchanging gases, heat, etc., with the atmosphere, the ocean forms a big sink. It can dissolve carbon dioxide. And so depending on how well oceans absorb carbon dioxide or release carbon dioxide, it can control quite a bit of global warming. And climate models, because they are often set at coarse resolution, they don't resolve all these large kinetic energy containing eddies in the ocean very well. So in many talks, we saw these coherent structures. So these are called eddies or vortices in the ocean. This is a satellite image showing us the chlorophyll distribution in the ocean. So this is an eddy. You can see small eddies here. So these eddies contain 90% of the flow kinetic energy in the ocean, and most climate models have often difficulties resolving these eddies and high kinetic energy structures in the ocean. So understanding climate dynamics on a longer time scale requires a very good understanding of ocean dynamics in the Earth system. So these are the equations that are typically solved. Many of you are familiar with these equations. So these are the Business equations. So we have equation for velocity. V is the three-dimensional velocity. B is the buoyancy. And so we have three equations here, one buoyancy equation and mass conservation. So here F and N are frequency associated with rotation stratification. And a key parameter that comes up in a lot of this is Rossby number. So Rossby number could be thought of the ratio of the fluid vorticity divided by the local rotation rate. So this tells you how strong the fluid at that particular scale feels the effect of rotation. So if your vorticity is much smaller compared to the rotation rate, Rossby number is small. This happens at scales we call mesoscales. So in the ocean, mesoscales are scales of the order of 100 kilometers or so. So in the previous slide, this eddy that we see here, this is of order 100 kilometer scale, 50 to 100 kilometer scale. That is what oceanographers call mesoscales. So 100 kilometer scale, mesoscale, these are the eddy scales in the ocean. And Rossby number at these scales are quite small. Whereas as you go to submesoscales, so we are reducing the scales, horizontal scales, by an order of magnitude. So 10 kilometer and below forms what are called submesoscales. And at these scales, Rossby number approaches order 1 value. So we have a transition in the flow dynamics from low Rossby number at mesoscales to order 1 Rossby numbers at submesoscales. Right. So now, again, from an Earth system point of view, a lot of people introduce the challenges in numerical simulations and resolving all these scales. So if you think about the oceans, so this is Earth systems. What they do, they discretize the domain onto along latitude and longitude and vertical. And so here is a set of scales we have to resolve in the system. So the smaller scales in the system, in the ocean, if you think about it, the centimeter or millimeter scale is where viscous dissipation happens. So this is the Kolmogorov scale. And the largest scale, this is what is often called the basin scale. It's 1,000 kilometer. That's the order of radius of the planet. That's basin scale. So between these two, there are about 8 decades of spatial scales, which needs to be resolved. And when you look at the time scales in the system, so in the previous slide, you saw rotation frequency and buoyancy frequency. Those fluctuations are associated with the fastest waves in the system. So dispersive waves in the system fluctuate with a time scale of order minutes. So that's the the shortest time scale you have to resolve to capture the dynamics, the fast dynamics in the system, and the long time scales if you're interested in weather. So atmospheric weather, you're looking at days to week, and the ocean, because ocean is slow, we're looking at months. So if you count again decades from minutes to months, we're looking at 6 decades of time scales. That's the order of time scales involved. And if you're looking at climate change, we talk about climate change order of centuries, more than decades, decades to centuries and so on. We're looking at 9 decades in time. So these are the scales you have to resolve if you are to keep track of the ocean as a whole from a dynamical systems point of view and from a numerical simulations point of view. But what is realizable these days? So people running simulations on high performance computing clusters, this, at present, we can relatively easily run solutions the order of 1,000, so 1,000 grid points in one direction, 1,000 in the other, and 200 grid points in the vertical. So this is a reasonably doable computation these days. And you can see, so this particular simulation will have, if you push it, we are looking at 3 decades. We are resolving 3 decades of spatial scales in a typical simulation, whereas in reality, you have to resolve 8 decades of scales to capture all the dynamics. And this is really short term. We're looking at weeks, at most months. But again, running climate scale simulations at this resolution is computationally very intense. So this is why keeping track of all the dynamics, all the scales, spatiotemporal scales, is extremely difficult. And that's where a lot of approximations come in. Can we model the scales that we don't directly capture, with some sort of parameterization? So now, looking specifically at ocean models, let me introduce some of the terminology. So ocean models, again, we heard this in many different talks. These ocean models are run at different configuration. They have different terminology for the model run at a particular resolutions. For example, there are eddy permitting simulations. So when they say eddy permitting, modelers mean the mesoscales are sort of partially resolved. So if you resolve the eddy field in the ocean partially, we say it's eddy permitting. And if you completely resolve it, it's called eddy resolving. So to have an eddy resolving simulation, you should have your grid size well below 100 kilometers. So you should have something like 50 kilometers, 10 kilometers, something. That should be a grid size. Whereas when you want submesoscale permitting, you're saying part of the submesoscale dynamics of the order of 10 kilometers, slightly below, partially resolved. So that's submesoscale permitting. And then we have submesoscale resolving, which means now your grid size has to be well below a kilometer. That's really pushing it. So submesoscale resolving simulations are extremely computationally intense. So now let's look at how these scales get resolved. So suppose you have a high resolution ocean model and it captures 3 decades of spatial scale. So what I introduced here in the previous slide here. So suppose we have a numerical grid of the order 1,000 by 1,000. If this is my resolution, then, and if I set it at basin scale, so imagine I have a domain whose dimensions, horizontal dimension is order 1,000 kilometers. So then I can say I'm resolving basin scale. So these cases are well resolved. Mesoscale is getting resolved if I have 1,000 grid points in each direction. But if I have 1,000 grid points, and if my grid size is order kilometer, then my submesoscales, which is order 10 kilometer, are still going to be affected by viscous effects. So in hydrodynamics, people learn this, that if you have viscous effect, their effects are felt up to a decade. So if you have viscous effects at 10 kilometer scales, they can corrupt 100 kilometer scales as well. So their effect can be felt up to a decade. So submesoscales are not going to be well resolved, even if you have a simulation that has 1,000 grid points in one direction, provided you resolve basin scale. You could do this slightly differently by saying, I don't want to resolve basin scale. I could start my domain at 100 kilometer scale. So if my domain size is 100 kilometer scales, then I can resolve submesoscales, because if I have 1,000 grid points, I can go up to 0.1 kilometer, in which case these submesoscales are going to be well resolved. So this sort of tells you in typical ocean models, if you resolve basin scale, which is important to capture a lot of the large scale circulation dynamics in the ocean, if you resolve basin scale, you don't easily resolve submesoscale. They're often viscously affected. So this is where parameterization comes in. Can we do something to resolve and model submesoscales? So this is a slide that shows how the dynamics of the ocean change as you increase resolution. So this used to be a popular exercise starting from a decade ago. So these figures are from Brannigan et al. And so here, and Keppe et al. This is another set of papers where What they do is they set up an ocean model and they gradually increase the resolution. That's all they're doing, increase the resolution gradually and see how the dynamics change as you increase the resolution. So this is at 4 kilometer resolution. You see you get coarse. So this is what is called the eddy permitting. You can see the eddies, but they're not well resolved. So this is eddy permitting. And as you go to 2 kilometer, now you're starting to see some of the boundaries better. This is 1 kilometer. Better, small scale structures are more energetic, and this is 0.5 kilometers. So you can see there's a lot of energetic small scale structure. So this, if you're a computational fluid dynamics person, this can be alarming because in CFD you talk about numerical convergence. So you say a simulation is converging if you increase the resolution, grid resolution, keep reducing the grid size, your solution should be independent of the grid size. That's when people say your simulation results have converged. But you can see in all these Earth system models, ocean models and all, you never get convergence in that classical sense. As you increase your resolution, more dynamics come up, and it's in a dynamic sense, you never really reach converged state. So this is showing the energy spectra that corresponds to these different resolutions. So blue is the coarsest resolution corresponding to this. And as you increase resolution, you can see the inertial range is getting longer, and you're starting to resolve more scales here. So you get a longer inertial range in both these. So these are summer and winter. You get longer inertial range with better slope. So you can see this particular, the steeper line is -3 and the shallower one is -5/3. So it goes from -3 to -5/3 as you increase resolution with these small scale structures emerging. So the key observations here is that the mesoscale flows have more or less symmetric vorticity structures. So these flows look more like 2D turbulence. Whereas as you go to submesoscale, we see a strong asymmetry. We see like positive vortices being coherent, strong, negative vortices get broken up, fragmented and filamented. So these are signs of active submesoscales and a shallower energy spectra. So you get more energy at smaller scales as you resolve submesoscales. And the challenge is these kind of, so for example, this particular simulation, they set it up with the regional model where they're not resolving basin scale. They're starting with mesoscale dynamics, and they're going finer to resolve submesoscale. So resolving all these scales in an ocean model where you resolve basin scale becomes a big challenge. So now at mesoscales, you have Rossby number small, and so you can do some approximation. So this is the derivation of what is called the quasi-geostrophic equation. So if Rossby number is small, you have a small parameter in the system, and you can exploit this system. So if you assume at leading order geostrophic balance, so you assume geostrophic balance, so your flow is completely in balance with the pressure gradient. So if you do this approximation, you can derive a single equation for the evolution of the balance component, this component. So that's the QG equation. And Professor Goswami, he spoke about the numerical weather forecast and the first revolution. He called it the first revolution, I think. So this is the first revolution. The first successful weather forecast used this equation because this equation is computationally much more easier to integrate than the full Boussinesq equation. So this was used, and so this is like the first successful weather prediction that used the QG model. So when you're at mesoscales, you can go with these approximations because you have a small parameter. But as you reach submesoscales, you don't have the small parameter. So Rossby number approaches order 1 values, and traditional techniques like asymptotics are not usable anymore in this scale. So this is where a lot of work is being done to understand and address many of these problems at submesoscales. So in this talk, I'll discuss 3 particular problems. One is predicting high modes from low modes. So baroclinic modes refer to vertical modes. So low baroclinic modes are coarser, can be obtained from satellite measurements and coarse resolution ocean models. So if you know low modes, can you predict high modes? So that'll be one of the questions we'll ask. The second one will be, can we come up with QG-like models? So we saw quasi-geostrophic equation that works at submesoscale when you have Rossby number small. But as you increase Rossby number and you go to submesoscale, can we still develop QG-like models for submesoscale? So that'll be the second question we'll look at. And the third question will be tracer dispersion. So along with the flow, tracers, there are a lot of tracers in the ocean, oxygen, nitrogen, all these are tracers. They have to be tracked along with the flow. Can we use some data-driven methods to address tracer dispersion at submesoscale? So these are the 3 particular problems we'll look at today. So let me go to the first one. So this has to do with predicting high baroclinic mode. So again, people who work in geophysics community know that baroclinic mode. So what we mean by baroclinic mode is if you take any of your field, and if you project it on vertical modes, so if your buoyancy frequency is constant, you have cosine and sine functions here. If you have a variable stratification and nonlinear stratification, you have some other orthogonal function here that comes up. But this is the idea of paracolonic projection. You project your function onto vertical modes, which are paracolonic modes, and structures that depend on horizontal and time. So when you look at oceanic flows, most of the energy lies in the first few vertical modes. Zeroth mode is called the barotropic mode, and first mode is the first paracolonic mode. And then when you go to higher modes, the higher modes typically contain very little energy. So that's something we know from observations. But although these high modes contain very little energy, when you have order 1 Rossby number flows, a lot of the dissipation that happens through these high modes. So high modes are very important when you want to keep track of energy dissipation of the flow. So this is something, again, that's observed when you have these eddies interact with topography, eddies interact with atmospheric winds, and so on. You generate a lot of these high modes. These modes have low energy, but they're dynamically important because they dissipate the flow energy. So this is, here's a model we'll use. This is a model where you keep 2 vertical modes of the system. So we have barotropic mode. This mode contains most of the flow kinetic energy. And then we have a very low barocolonic mode, which this is a high barocolonic mode. So this is a 2-mode model. This is a model. So it's similar to the shallow water equations that people use in the geophysical community. Very similar to shallow water equation, with the difference that instead of writing the equations in 2 layers, we are written in terms of 2 modes. So this is the decomposing, for example, vorticity decomposed into a barotropic component, which is uniform in the vertical, and a very high N, a very high barocolonic mode. So this is now, we're generating a series of turbulent flows with this model. So we have order 100 flows, where this red is showing us the energy of the barotropic component, and the blue is the baroclinic component. And here, so here I'm showing you the histograms of the vorticity field from low to high Rossby number. So the lowest Rossby number is this red one. It's you can see the histogram is almost symmetric. So this corresponds to this kind of a vorticity structure, where you have more or less equal positive and negative coherent vortices. And this is the corresponding baroclinic flow. Now, as we increase Rossby number from top to bottom, you can see these positive vortices, they shrink in size, and a lot of the negative vortices get destroyed. They form a background soup. So the PDFs, the histograms of the vorticity field now, you can see it develops these fatter tails towards the positive direction. So you can see the black one, there's a long tail to the right, whereas here it's still relatively low value. So this asymmetric vorticity field is a feature of these submesoscale turbulent flows. So this is the barotropic flow, and this is the high baroclinic field. So this component, as shown here, this has very little energy compared to this barotropic mode. And we are asking, if you know the barotropic flow structure, if you know this, can you predict the structure, high baroclinic structure? So for this, this is work with a student called Mausam. So we're using, in the morning talk, speaker introduced GAN. So we're using a GAN, and we're using a specific form of GAN called conditional GAN. So this GAN, or CGAN, it takes in these 2 inputs. It takes Rossby number. So we are, from the previous figure, Rossby number is changing from top to bottom. So that's Rossby number. And we input the Rossby number and this barotropic vorticity field. These are the inputs. And given these 2 fields, at low vertical mode, we want to predict this high vertical mode baroclinic structure. So this is the CGAN. So, I think we will have some machine learning tutorials as part of this, or no? Yeah, there will be. Okay, so I just put some of these figures. If you're familiar with things like unit, and also a unit is this kind of an architecture. So if you flip this, if you rotate this 90 degrees, it looks like a U. That's why it's called a unit. So unit is the what forms a generator of GAN, and then it has a second component called discriminator. So the GANs can be trained very well to identify and predict some of these complex images, especially when you have small scale structures. Training GAN is a lot of pain, but if you know this well, what you do is you can work with the generator, train the unit to a good extent, and then you bring in the discriminator. So the generator will output some predictions, which the discriminator will check and will will approve it or discard it. So this back and forth between generator and discriminator can help you capture some of the small scale structures in these turbulent flows very well. So GAN is very useful for some of these turbulent structure predictions. So typically in a neural net, you have, this is what is happening, right? You're putting in an input, it's multiplied by some weights, added biases, and then you get an output. And there will be a loss function, which will be tested against the truth. So you're checking the truth against the neural net output, and this is minimized. So in GANs, you'll have loss functions coming from the generator and the discriminator, and they couple. So the generator loss function will have contribution from discriminator loss function, they couple. So you can minimize it to get the small scale structures predicted very well. So here, in the previous slide, I showed about 91 flows. So if you look here, so these are the 91 flows. So we're putting in, out of those 91 flows, we're only using about 25 of them to train this, to minimize this loss function, and then the rest are used for predictions. And this particular architecture, so this is called a CBAM unit. So this is recently used for coronary angiography. So these guys came up with this kind of an architecture that gets some of the small scale features well for their work. So we kind of adapted that for this turbulence problem. So here we're looking at some of the predictions now. This is the horizontal velocity in x direction. So this is the truth, and this is a prediction from the CGAN. And this is the horizontal velocity in the y direction. This is again the truth, and this is like the GAN prediction. So this is an example prediction, and this is showing us the PDF. So this is a PDF of these guys. So the true PDF is the black one, and the neural net prediction is the red one. And this is showing us the baroclinic flow energy spectrum. So again, the black is the truth, and the red is the neural net prediction. So the predictions are in general very good. So when you look at, so this is just one case. So we took all these predictions and did an ensemble average. And the advantage and utility of neural nets comes here. So as explained in the high baroclinic mode is very difficult to track in observations or models. High baroclinic modes are not well resolved. So if we can predict high baroclinic modes from low modes, that's a big advantage. So here, when we look at the predicted dissipation of the high baroclinic mode versus the actual dissipation, we are able to predict about 90%. That's a great advantage. And the predicted energy of the high baroclinic mode versus actual energy, so both are about more than 90%. And so this is good because the high mode dissipation is very hard to keep track of in these coarse resolution models and observations. So satellite images can give you low mode structure. Getting high mode structure is very hard. So these are very useful outputs that these neural net predictions can be used to calculate. So yeah, so there's a poster by Mausam outside that explains a lot of these details more. And so this is, in the interest of time, I'm skipping some things we did with equation discovery. So again, in the morning's talk, Vishal spoke about equation discovery. For this problem, again, we can apply equation discovery and you can get some predictions. Rather than rely on neural net, you can get explicit equations. So that's sort of explained in Pustam's poster again outside. So that's one problem that I'll discuss today. Now we'll go to the second one, where the goal is to come up with a dynamic model. So for submesoscales, can we come up with QG-like models that we can evolve in time? So here, this is showing us the sea surface height spectrum from Richman et al. So if you look at the spectrum, the black curve here is the total spectrum, and this is being decomposed into a high frequency spectrum, which is this red one, and a low frequency spectrum, which is this blue one. So what you see is, so submesoscale starts around here. As you go to submesoscales, the low frequency component or the eddies can get weaker, whereas a high frequency components like internal gravity waves and other components can get stronger. So this is something that's observed in many regions. So these are a lot of observations and model outputs that point to this. So as you approach order 1 Rossby number flows, your wave field or unbalanced components can be much stronger. Yes, so now, again, recall QG equation. So if you think about the Cauchy-Joseph equation, this equation has two conserved quantities. One is energy, so this is energy, and the second one is entropy. So entropy is this potential vorticity squared integrated to the domain. Now, because of these two conserved quantities, the flow kinetic energy goes to larger scales with time. So this is the inverse energy cascade. So if you look at this particular movie, this is showing us a simulation of the balance dynamics, where you can see these big vortices form and they get bigger with time. So this is the inverse cascade of energy going up. Now this is very similar to the 2D vorticity equation. So here's the 2D vorticity equation, where again you have a vorticity dependent on the stream function by Laplacian. And here again you have conservation of energy and entropy. So it's the QG dynamics is qualitatively similar to this 2D vorticity or 2D turbulent dynamics. But when you go to submesoscales, you can have different kinds of scenarios like this. So you can have regimes where internal waves can completely destroy your vorticity structures. You can get structures like this. So this is the QG kind of regime. Whereas if you have a lot of waves, it can generate small scale structures and high dissipation. And as we saw in previous slides, you can have this transition as you go from low Rho to high Rho. Large symmetric coherent structures going towards asymmetric structures with high positive vortices and broken negative vortices. So flows like this with asymmetric structures, can we modify the QG equation to get a model that can capture some of these features? So that's the question we're asking here. So to see this, we'll stay at low Rossby. So in the low Rossby number regime, this is a kind of equation that's been derived in many different papers in the past. What you do is, so QG equation is an equation that's derived to leading order in Rossby number. So it doesn't have Rossby number explicitly in it. So if you remove the blue and red terms here, you get the QG equation. But if you go to higher orders asymptotically, so if you go to next order, for example, you get Rossby number dependent terms. So this is sometimes called the QG plus equation, the next order correction to QG. And it was first derived by Allen. So all these papers derive it in different forms. So Allen derived it in shallow water models, this QG plus equation with some of these extra terms. But the important thing is you have these nonlinear wave-wave interaction terms, internal gravity wave contributions coming in at next order. So this is how the equation looks. So we're going to take inspiration from this model. This model is derived asymptotically in this regime Rossby small, but we're going to modify this equation or take inspiration from this and derive a model that works on Rossby order 1 regime. So the first step is we're going to put in an external term. This QS is a term which is in general stochastic. So this term can have a structure that evolves in time, and it has a spatial structure which we enforce. So for example, this is how it looks. So QS is Laplacian of S psi s, and psi s is like a stream function which we specify. So you have a random coefficient times k to the power minus b. So b is the external field. So this QS is an external vorticity field which we specify, which is mimicking the effect of these unbalanced flow components. So we put that in. This is our modified QG equation. So in general, you can model this QS as a stochastic term with a separate stochastic differential equation. So we have gone with, you can use simple Brownian motion, complex Ornstein Olympic process, or more SDEs that you might not be able to explicitly analytically solve, but you can numerically time strip this. So this is the modification to QG, the first modification. So if you do this, you can show that the way this equation is written, we still have energy conservation. So energy is still conserved, but we've lost entropy conservation because of this extra term. Now Q square integrated of the domain is not conserved. And so this gives us a model which conserves flow kinetic energy, but no conservation of entropy. And so depending on how strong this particular term is, this QS is, we can define the strength of this external term that we put in, the strength of the stochastic term. We can define an energy associated with that term. And this ratio of the energy associated with this external term to the energy associated with the psi of that we are evolving is R. So R, when R is very small, the effect of this external term is going to be small, whereas when R is large, we are introducing a big perturbation to the equation. So how does this model perform when we increase R? So here are some snapshots of the vorticity field with increasing R. So here R is extremely small, 10 power minus 5 or so. This looks like 2D turbulence. Now as we increase R, so this is R1. When R is 1, you don't get any coherent structures. But for intermediate R, you get flows that have coherent structures and some small-scale structures. So this is showing us the energy spectrum for different R. So as you increase R, you can see the spectra becomes shallower. It goes from -3 to -2. And this is showing us the energy flux. So at the lowest R, see, this is the inertial range. So in the inertial range, the forward flux is almost 0 when R is small. So it's pretty much 2D turbulence with an inverse cascade. Whereas as we increase R, you get stronger and stronger forward cascade and a lot of dissipation. So that's what happens as we increase R. And this is so this is an interesting feature for turbulence enthusiasts. In 2D turbulence, we don't have something called intermittency. So intermittency is something that's missed in 2D turbulence, and this is often measured by, this is one way to measure intermittency. You plot what are called structure functions. So structure function is defined as the velocity difference between 2 points. So R is the separation between 2 points, and you do an ensemble average over all different x's. You get the velocity change between 2 points separated by R over the entire domain. So this delta VR, if you plot it as a function of R, in 2D turbulence, the distributions of these delta VRs, they almost overlap. So which means the velocity structure function is sort of independent of the separation. So that's when people say there's no intermittency in 2D turbulence. Whereas in 3D turbulence, if you plot the structure functions, they look very different at different scales. So this particular model at very high R, so I think this corresponds to R4 flow, this particular flow, you can see that at the grid scale, delta x, so this is structure function computed with delta x, you get a fatter tailed distribution, whereas as you go to domain scale, large scale, you get something that's close to a Gaussian. So in both these, the dotted lines are a Gaussian. So this is how 3D turbulent, 3D homogeneous isotropic turbulence structure functions look. So in these flows, we are having a transition from 2D-like turbulence with no intermittency to a flow that looks more like 3D and has intermittency. So now so with this model, with this external term, can generate flows like this, can generate this sort of a transition. But how do we get to things like this, where we're going from this more or less equal distribution of positive and negative vortices to an asymmetric vorticity structure? How do we get that? So to get that, we go back to this previous equation again. And in this particular equation, I didn't write down the explicit terms, but there are a lot of terms here. So these are eddy-eddy interaction terms, which are composed of a lot of these quadratic nonlinear terms. So what we do is, this is where we use an equation discovery kind of algorithm, where we say we want to look for a perturbation here. So we're modifying QG equation again with this epsilon f. This f is a term that we're going to pick from a set of functions. So that's again inspired by the form this term looks like. So this term has terms of this form: stream function times vorticity, vorticity square, and all these. There's like a lot of these quadratic nonlinear terms. So we put in all these terms, and so this is an equation discovery kind of procedure. We were saying we want the term that produces asymmetric vorticity structures. We want positive vortices to dominate. So when you look for that, surprisingly, this particular term does the best. There were other terms that comes close, like such as this, but Q squared was the simplest, nicest looking term that can produce dominant cyclones and asymmetric vorticity structures. So this is how the model does when we put in this Q square term. So this is the full model now, and we call this the submesoscale 2D vorticity equation, S2dV. So here we have the usual time derivative term, stream function. So QG will stop here, but we have this external term and the Q square term. So with the strength of this term is quantified by this epsilon in front of it. So we can control, so we have two control parameters. One is R, which measures the strength of this term, and epsilon measures the strength of this asymmetric term. So when both are 0, you get 2D vorticity QG-like dynamics. Set the external term to 0, just keep this external, set this to 0 and just keep this Q square term, we get these big positive vortices in a soup of negative vortices. And if you keep both terms and if you control them, you can get flows like this, where you have a big coherent structure which is positive in a broken background of positive and negative vortices. And this is how the PDFs of these three flows look. The black one is the symmetric one, it corresponds to this one. Blue is for this one, and red is for this one, where you get this fat tail towards the positive direction. Now this model you can tweak to generate complex flows. So here, let's go back one slide. Here, as I said, there are two terms we can control. Epsilon controls the asymmetry term. R controls the strength of this external term. So by tweaking them, we can generate flows that resemble complex flows. So here, for example, this is from a non-hydrostatic busyness simulation, this flow. This is the corresponding S2DV match. And this is from an ocean model. Dedizio et al. Is there. This is you can see it's latitude and longitude. So it's a big ocean model. We're taking snapshots of these model outputs, and we are tuning the two parameters of the model to generate similar flows. So this is from Siegelman 2020. Again, you can produce similar flows. This is again an ocean model it's a Mediterranean Sea region, and S2DV produces similar flows. So you can see how you can tweak this model to generate complex ocean model outputs much cheaper. You can run, so these models, you'll need thousands of processors on supercomputer. This you can run on laptop. So here we are looking at the PDFs. So this is, so for three of the flows that I showed here earlier, these are the PDFs. So this is the, I think the complex one is red in all these cases, and S2DV PDFs are the ones in blue. So the PDFs also match pretty well for those flows that I showed. And we can do more. If you look at the energy flux, rate of cascade and all, you can match them also with those tuning parameters. So this is a useful model, can generate these asymmetric flows, and it can match complex ocean models. And it can be used for, there are a lot of utility for flows like this, because oceanographers, so ecosystem modelers, biogeochemical modelers, they need flows that can stir planktons and so on. For those, they often rely on these complex ocean models for the flow. So you don't have to run ocean models if you just want to run an ecosystem model or a biogeochemical model. You can just generate flows from S2DV and use that to stir tracers like planktons. So more details you can find in this paper. So that's like a second question on data-driven utility for submesoscales. Now we look at the last problem briefly, and this has to do with tracers. So the flows in the ocean, they're not by themselves. There are a lot of tracers that go into these ocean models. So we have heat, salt, carbon, oxygen, nitrogen. All these are tracers that have to be evolved along with the flow. And the tracer dispersion, so you're integrating an equation like this. Theta is a tracer. So this is a passive tracer. Theta is the passive tracer. It's being advected by the flow and is being dissipated by this diffusion operator. So when you use ocean models, what people generally find is this alpha, this ocean, this tracer diffusivity is something that you have to set in an ocean model. And depending on what you set, it can change the flow dynamics and tracer dynamics a lot, because all these are coupled. So for example, lateral diffusivity can affect your strength of ocean circulation, ocean's uptake of carbon. All of that can be affected by alpha. So it's very important to model this well, or have very good predictions of this tracer field. So now, again, in this context of submesoscales, what people find in general is, when you go to submesoscales, so again, people who know a little bit of tracers know that if you put a tracer in a more turbulent flow, there's stronger dispersion of the tracer. So submesoscales, because they have a lot of energy at small scales, tracers get better stirred at submesoscales. So the diffusivities of the tracers you find is much stronger than what you expect based on mesoscale-based theories in the ocean. And so with oops, I think my laser is gone. So with a lot of these complex numerical simulation that resolve submesoscales, you can capture tracer diffuse. So these are some of the papers where we explain how submesoscales has higher diffusivity and tracer stirring than mesoscales. But now, from a data-driven perspective, so these are papers where we are integrating non-hydrostatic Boussinesq equations and all to get tracer dynamics. But we're asking, can we skip the tracer equation, what I showed in the previous slide? Can we completely skip the tracer equation? And can we directly predict the tracer from the flow? So here, this is work done with Kumar, PhD student here. So we are looking at, these are the different neural net architectures. So Mayank has a nice poster outside where he explains all this in detail. So we went with 4 different architectures. The simplest one is autoencoder. This is a unit. So as I mentioned earlier, you can see this U-shaped thing. And unit acts as a generator. If you put a discriminator also, the combination produces a GAN. So we have a GAN. And this is a new model which Mayank was able to design. So what it's doing is the following. So typically if you look at a convolution layer, we have, so you can see there are those on the right, those are weights. So as this window moves, you're essentially training for these weights. These weights are typically fixed in a 2D convolution layer. You find the optimal weights in this convolution layer. But in this thing that we call local convolution or locone, as this convolution window passes, you can have different weights in this process. So that creates what is called a locone. So locone is essentially a unit with these extra parts added. Okay, so these are called the locone layer, which has this particular feature in it. So these are the 4 neural net architectures we experimented with. And again, so we're producing about 40 different dynamic regimes. The table shows red ones. Red ones are 14 regimes we use for training, and the rest 26 are used for prediction. And the loss function, so here's the loss function. It has 2 parts again. This part, the first part is the L1 loss, and the second part is what we call the spectral loss. So in these tracer predictions, we want the small scale dynamics to be well predicted. So the spectral loss, the second part of the loss function, helps to pin the inertial range part of the tracer variance better. So we're enforcing conditions here. And this is sort of like physics-informed neural network pin, where an extra condition is put into the loss function. So now what is the advantage of these kind of neural nets? So if you compare the time taken for direct integration. So if I integrate a tracer equation so the red marked cells here are used for training. 26 of the remaining white ones are used for prediction. So to generate those 26 white cells, tracer fields, you would take, if you compare direct numerical simulation, you'll take about 81 hours. That's written up. Now, if you look at these different neural nets, we'll see that the locone is the best model that's suited for this work. You can see we are looking at 1.6, 1.8, 3, and 4 hours for different neural nets. So this neural net can predict the tracer field 45 times faster than direct integration. So this includes the training time also, all these times. So we are adding the training time and the prediction time. The neural net significantly beats the time you would take for direct integration. So that's a great advantage. And you can read again more details in this paper and on Mayank's poster. I'll just show some of our results. So this is again the tracer physical structure. That's the truth. On top left, top right, that's the lock-on prediction. So we put in these black boxes where you can zoom in and see small scale structures better. So the truth, you can see truth has a lot of these fine scale structures. So here, this left is without the spectral loss. So we are just going with the L1 loss. And when we go with the L1 loss, you can see the tracer predictions. So black here is the truth. The rest of the spectrum, you can see the tracer spectrum falls off after a point. So when you put the spectral loss in, that's the right predictions. When you put the spectral loss in, the tracer variance spectrum better aligns with the truth. So the left and right, this is without spectral loss, that's with spectral loss. If you look inside the boxes, so unit, autoencoder, and GAN, they don't do a great job in resolving these fine scale structures, but this lock-on model does much better, and particularly in the spectrum. So when you look at the spectrum, black is truth, yellow is locone. So locone does a very good job, especially with spectral loss, in aligning with the true tracer spectrum. So that was the tracer field. Now this is showing us the trace of flux. So flux now is a derived quantity. So it's predicting, getting the flux correct is a bigger test for the neural net prediction. Again, this is now showing the truth, that's locon. And so you can see all the models are sort of faded when you look at the flux. And this is the distribution, PDF of the flux. Again, black is the truth and yellow is locon. So all these models overshoot at low values of flux. But when you put in this spectral loss, what you see is that the locon does a much better job. Again, top left is truth, that's locon. You get small scale structures better predicted with the spectral loss. So these are, so now there are consequences to the spectral loss. Some of the other models like unit GAN and all, it shows these small regions. There are these localized regions where flux becomes very high. So this follows from the predictions also. When you look at the predictions also, when you put in the spectral loss to force the tracer variance to higher values in the inertial range, you often generate these artificial small scale structures in the prediction in some of these models. Whereas locon doesn't seem to do that. Now, and because of those artificial small scale structures, when you look at the flux now is differentiating the tracer prediction. So these small scale structures get accentuated when you go to the flux. So you can see that in unit GAN and all. And now the distributions also, black and yellow. So black is truth and yellow is the locon one. They align reasonably well. The other models again overshoot in the low flux region. Okay, so maybe I'll conclude with that. So now, as mentioned from the beginning, submesoscales is a very energetic scale of ocean dynamics where the models don't resolve these scales very well. So Rossby number approaches order 1 values, so we have trouble resolving them. And because we don't have a small parameter, it's not easy to derive asymptotic models and all for these kind of flows. So this is where there's a lot of work going on with data-driven models. So I presented 3 kinds of problems where we could use some of the data-driven techniques. One was to predict high baroclinic modes. If you know low modes from models or observations, can you predict high baroclinic modes? And we were able to show that with this GAN, you can predict spatial structure, dissipation, energy of high baroclinic modes from low modes. And the second problem we looked at was a dynamic model for submesoscales. Can we develop a QG-like model that works at submesoscales and can produce small-scale rich asymmetric vorticity structures? So that was done with this combination of equation discovery and some stochastic tools. And the third one was, if you know the flow, can you, without direct integration of the tracer equation, can we directly predict the tracer structure, tracer flux, and so on? So that was done with this specialized locon neural net, which can predict the tracer structure and flux. And it's, as explained, you save a lot of computational resource without having to directly integrate the tracer equation by directly predicting the tracer with the flow. So I'll stop there.
Okay. Thanks a lot. Thanks a lot, Jim. Questions from the audience? Questions? People too sleepy after lunch? Okay, Vishal.
Yeah, thanks, Jim, for the nice lecture as always. My question is actually, see, ultimately, the equation that you are solving is a subset of the full Navier-Stokes coupled with phenomena.
Right.
How much of the unrepresented part affect, say, for example, tracer flow, tracer transport, or
Right.
the small scales that you see?
Right. At present, there's no feedback. Right. Everything I presented is one way, sort of. If you know the large scale dynamics, we are trying to predict the small scale dynamics, but the small scales are not coupled back. That needs more work. That would be the answer. For example, submesoscale dynamics do affect mesoscale dynamics because sometimes they pass energy upscale. So that is not being represented here.
In this, the varying background state is considered?
Varying background with
State from which the energy is taken up,
uh,
or it's fixed?
no, we are putting the background state is assumed to be independent of the small scale dynamics, so it's being specified.
Right. Right. But is it a function of time?
It is a function of time, yes.
All right. So for the last work where the, I mean, you said the application is to figure out traces, right?
Yes.
So the low cost models, the machine learning models, could they be used? For example, I have this, maybe we have 5 minutes. Maybe I'll say in a line or so, we lost this Malaysian Airlines flight, right?
Right. Yes.
Assuming it fell somewhere, the problem of finding out what are the most probable location was pursued by people.
Right.
So I was thinking, can such a method be used in such applications?
Yeah, if you have enough training data, hopefully that doesn't require more.
I mean, is it actually? I fully couldn't understand which parts of the scales are resolved right now. Submesoscales
Submesoscales are resolved.
are resolved.
Yeah.
So if we were to know exactly, let's say within some error bar where the flight, I mean the flight was lost, where it assuming it landed in the ocean, could this sort of a method help you narrow down? I mean, is there enough structure in the submesoscale
Yeah, so
flows for us to give us
yes.
some more insight?
If it isn't, oh, you're saying if the flight landed in the ocean,
Yes.
in that situation, yeah. Well, if you have, I have to think, how would you train that, right? If you have the right flow structures, and so you want to do an inverse problem, right? If it landed somewhere.
I mean, in this case, in this particular instance, some bits and pieces of it were washed as ashore in some places. So
Right.
yeah, so actually, as far as I know, some people actually ran some ocean dynamics models that if it landed in such, if it crashed in such and such place, is it visible that some parts will float? So this is like the inverse problem, that given that some things did wash up here, then can we figure out where it landed?
Sounds like a state estimation problem.
Yes, it's something like that. There is one online question. In the Locon model, your aim was positionally varying convolution weights. At this stage, would attention be better? And I mean, attention-based models, would that be better? Additionally, how is Locon parameterized? Is it a neural network which predicts the kernel weights? And another question is, like in practice, given that we are predicting a parameter which we know is constrained in some range, how can we constrain the network output?
Yeah, I mean, so the questions about neural nets in general, right? So a lot of these, the two works that I presented, what we did was, we're starting with the simplest models. So for example, autoencoder, in the previous one, before we got to GAN, we were starting with simple ANNs, and we upscaled them. And so, I don't think any of these neural nets are unique in that sense. This is like one solution to the particular problem. You can always come up with other solutions. These are also models that are relatively small. So for example, Locon is an attempt to keep the model small but vary weights. You could throw in a bigger model with a lot more parameters. You could do things like that. So, I think the question is coming from that angle. Is this sort of unique or specific to the problem? No, we could come up with different models. And the way we approach all of this is you're starting with the simplest you can, and you're adding complexity to see what is the minimal set that can give the result you need.
Okay, there is like one question related to, like, can you please explain once again the spectral loss function, or if possible?
Yeah, the spectral. Okay, so let's look here. So this is, for example,
no, the loss function itself. Maybe I think the
not just the spectral loss. Yeah, so let's look here. See, this is how the prediction looks. So black is the truth, and let's take the green. Green is the GAN prediction. You can see the prediction is falling off after wave number 10. So in the truth, we have an inertial range that goes beyond 100, but the prediction has its spectrum falling off after 10. So what we do is, in the loss function, the first part is this is the L1 loss, the usual thing, and we are adding a lambda, a parameter times this part. So what this is doing is it's subtracting. So this double tilde, so what it means is you're taking the tracer. So you're taking the tracer and you're retaining only this part of the tracer. You're removing everything else, just keeping this part, the inertial range part. So that is being subtracted. So we're subtracting that from the truth and prediction and taking the log of that. So taking log brings it up because it's a decaying thing. Taking log brings it up. And so this is a way to enforce that the prediction spectrum, the inertial range part, is forced to match the truth. So that's the spectral loss part. So you add both these things with this parameter lambda, and you can control lambda. So again, if you read the paper, you'll find that one of the things we figured in the paper is changing lambda. So by changing lambda, you can find an optimal lambda where the predictions are best. So everything I showed was for an optimal lambda. If lambda is too low, your spectrum continues to decay. You don't get the inertial range well. If lambda is too high, that also leads to artificial issues in the predictions. So we find this optimal lambda with this, and yeah, that's the loss function.
Sir, in the CGen slide, you said that you generated 91 flows, and out
Yeah.
of that, 25 were used to train it, and the others were used to test it.
Right.
Right?
Yes.
So, I have a question. In general, when you have data, more data is used to train it.
Right.
Yeah. So, why did you use only 25 out of those 91?
Yeah, so that's
you
a
generated?
feature. That's a very good question. You know, that's a feature of all these things. If you look at these kind of flows that we're dealing with, these flows have coherent structures. There are these filaments. There are distinguished features that stand out. And so also you can see this is the 91 flows. So they all have distinct features, and because of that similarity, we often end up using way less regimes for training. So we're looking at a particular, for example, again, you can see the energy. This barotropic energy is the red one. That's in that range. Baroclinic energy is here. So we're looking at flows that have the ratio more or less constant. So that sort of fixes a lot of features for these flows.
Quick question. So in the first part when you represented the scan F,
Yes.
so was scan the only failure model, or did you try some other utility model?
No, yeah, there were, in fact, unit sort of did well, but not that well. So again, we started with simple ANN and let's see where it is. No, we started with an ANN and this model was again an adaptation of this, what these guys did. Unit alone was not doing very well with the small scale structures. So these guys put up this model, which we adapted for this. So no, CGAN with this structure gave predictions that were reasonably good, especially this spectra and this part. So again, in this particular problem, we really want the dissipation range to be well resolved in the prediction. So that CGAN did a good job. And interestingly, for this problem, so we didn't need spectral loss. Spectral loss wasn't doing more. Even without spectral loss, small scale structures were well resolved.
Okay, so let's thank Jim for this excellent talk. And